I have bad news and I have bad news. The first bad news is that whoever tried to ask me about Nvidia shares and ask me if you could buy it or sell it, I have no answer for you. So that's the first bad news. The second bad news is that I am actually a scientist. I'm a trained mathematician, a computational scientist, and I happen to get into artificial intelligence by accident. I work for Nvidia. I run the global Nvidia AI technology centers. At the same time, I'm also a professor in a couple of universities. Now, like I said again, my background comes from science. So I'm looking from the angles of science itself. And one of the things is that science we have a lot of problems. One of them is climate change. We are seeing a lot of drastic climate changes and whatsoever, as you guys could see over here. And then here over all the extreme weathers, typhoons, heavy rains, and so forth. There are also many other problems which we could see, and this is from the IPCC ARC reports. You could see that the Earth is actually warming very, very quickly. Now, there are also many other problems. One of them is energy. We need more energy because of artificial intelligence and because of not just artificial intelligence itself, but because of many other things that we need actually energy. The industry cannot progress on, especially with the technology world, we do need more energy, so to say. The other thing is food security. Food itself is become more and more challenging for many countries as we change in weather, as we lack of water and lack of technologies, lack of energy itself. And lastly but not least is actually healthcare. So these are one of the there are many other problems, but these are one of the major key problems that as a scientist in my groups are actually focusing on. Now, when we look at how a scientist works, and this is what usually a scientist, this is a flow chart of a scientist. You have observations, you have research topics areas, statement of hypotheses, and so forth and so forth. And usually, the human is the bottleneck. That's why at the end of it, you wait for a long time to actually get the answers or get a thing. So this is one of the bottlenecks. So can we actually look at machines to actually help us to solve some of these problems, to actually increase the productivities and so forth. And not just increase in productivities, but getting machine to make new discovery. And that is a challenge, right? So in the healthcare itself, as you guys would know, places like I visited quite a fair bit. In China itself, they are using huge amount of data, and they have actually Tsinghua University has built a AI hospital, which actually mitigate or rather reduce the amount of waiting times for the patients and so forth. So healthcare is taking a lot of inputs or rather technologies from the artificial intelligence community. Now, this is typically what a AI scientist would do, right? What we want them to do is from AI for academic survey, for this science discovery, writings, and so forth. So these are basically what we envisage, or rather what we dream of having an AI scientist would do to help us. Now, so we turn back to the climate model. How do the climate scientists actually do climate science right now? Now, there are many things that you know that the problem itself is chaotic, there are incomplete observations, finite resources, and whatsoever. And let us focus on one thing, the resources. Now, for those of you who are doing climate science, you will know that at the current way we are doing climate science itself, and this is where we are at the moment right now, that is at a 1 kilometer resolution, or rather 1 minutes resolutions. We need roughly about a very large compute portion if we normalize it to 1 right now. If we want to model the Earth at a high resolution, as we go by at 100 meters, it takes about 10,000 times of what the current supercomputers is needed. If you increase it to 1 meter resolution, basically 1 meter resolution, right? In order to predict those weather at 1 meter resolution, you need about 100 billion compute power of the current size of a supercomputers. And that is the case. So this is not doable. We need to find new science, we need to find new math, or we need to find new ways of doing it. Now this is where I come from. A small little island called Singapore. The red dot is not very pretty aligned, but it's 1 degree north of the equator. Slightly, much smaller than Greece itself, right? Maybe the size of Athens. In Singapore itself, it is smaller than, if you look at the square, Singapore itself is smaller than that particular resolutions. So in order for us to simulate that, just we've got to do local simulations. And this is the case, right? And Singapore is an extremely warm island. Not because it's 1 degree off the equator, and because Singapore is a highly industry country, island. Everywhere is manufacturing, semiconductors, pharmaceuticals, offices, or whatsoever. 6 million people in a 700 square kilometers area. Now, to do the science itself, don't worry about the equations, but I just want to impress on you. To do the science itself, of the climate science, it basically is just a Navier-Stokes equation. Now, as you guys may know, the Navier-Stokes equation has been existing for the longest period of time. And one of the things is that we need to discretize them and put them into the computers in order to run them. Right? In traditional computers, whether it's GPUs or whatever, we need to discretize them, partition them, and then run on them. However, like I said before, it takes a very long time to actually run those simulations. So what we intend to do is that can we find a way of finding a surrogate model? A surrogate model basically means that you're actually mapping from one space to the next space. And this is something what we call physics-informed neural network. And for many of you who have heard about something called, all about the neural network, about having a lot of data, physics-informed neural network is a combination of using the traditional physics equation together with data, training the neural network to understand the physics itself, right? And this is one of the experiments we have done with Siemens.
Total worldwide wind energy capacity currently exceeds 750 gigawatts and is growing faster than ever, with an additional 650 gigawatts to be added in the next 5 years. For companies like Siemens Gamesa Renewable Energy, optimizing the configuration of each new wind farm is critical for getting the most out of their investment and reducing costs for consumers. When designing a wind farm, it's critical to place each turbine so as to minimize the effects the turbines have on each other due to the wake that they create. Accurately modeling the wake requires high-resolution, high-fidelity simulation data that is specific to that wind farm, such as the geographic location and the terrain. The gold standard for generating this data is the large eddy simulation shown here. But to run just one iteration for a single turbine can take 40 days on a 100-core CPU. And with so many iterations needed to develop an accurate model for a specific site, using CPUs is impractical. Using Nvidia Modulus and Nvidia Omniverse, Siemens Gamesa has been able to reduce that 40 days to just 15 minutes, approximately 4,000 times faster. This is accomplished by running the model at a lower resolution, and then, with a physics ML model trained using Modulus, to enhance or super resolve.
So for the sake of time, I'm going to cut short that a little bit. But basically the whole idea is this, is that what we do is that instead of using the traditional physics that we know of, we actually embed them into a neural network and allow the neural network to do the prediction for us. And once we train that neural network, we can then predict it in a very, very quick manner. And this is one of the examples. It is about, for that examples, it reduced the computational times by 40,000 times. But is it enough? It is still not enough, because we need 1 million times faster. We need almost a couple of 100 million times faster in order for us to do what we call the Earth simulation models. And so works still need to go on. We still need to work together with the research communities and so forth to develop new mathematics, new neural nets, and so forth. But just let's switch attention over to here. Over the last couple of years, AI has been progressing tremendously. Now, there is basically I generally distinguish between two types of artificial intelligence. One of them is predictive, the other one is generative. Well, the predictive side of artificial intelligence has surpassed humans tremendously. Things like facial recognitions, things like image processing, image recognitions, and so forth. And it has surpassed human in a very surprising way. In fact, over the last couple of years, if you see the rate of acceleration has gone up tremendously. And the important thing is that the reason why we did not enter into AI winters, especially on the predictive side, is because there are a lot of applications, and there are a lot of companies building up all these applications. From facial recognition, for those of you who have come to Singapore airports whatsoever, you can actually walk through without having to show your passport and whatsoever, just having a facial recognitions and stuff like this, right? These are examples of a predictive thing. Well, sports used to be, you need to have a referee to actually count the number of punches. Now you have things like this, right? Now, so to switch over, now you hear a lot about generative AI. Now, generative AI is not just about ChatGPT. It consists of many things. The whole idea, the whole concept of it is that you have a lot of these data itself. You create artificial intelligence, you train the artificial intelligence and encapsulate the probability distribution of it, and then you use it to do your image generation or data generations. One of the earliest applications, and then this is what you always see, like things like runways, stories, whatsoever, that allow you to generate out all these images. The concept is very simple. It just uses physics, the whole idea of physics, where you use fluid dynamics, diffusion models, and feed it into a neural network, feed it forward in one way of the neural network, and then train it to reconstruct it back in the other way. Do not worry about it too much, but it has many, many different applications. Switch topics over here is that what you mainly hear of it is the classical large language models. The large language model itself has been, natural language processing has been around for a longest period of time. Right? For the last 30, 40 years, people have been researching about it until the last couple of years when neural network, and especially in 2017, where the paper, Attention is All You Need, is published, that actually changed the entire dynamics of the natural language processing space. So there are a lot of models that have been produced, and so forth. But I just want to give you an idea of what is a natural language processing, large language models. The large language model itself is simply a mathematical model, statistical mathematical models that allow you to predict the next word based on the input that you have and the output that's generated by the models, and then it is auto-recursive models. It generates out the things. So the thing is that when we see all these interesting emerging phenomena coming out from a large language model, its ability to reason, the ability to do many other things, all these things are not originally designed in the language models. It is an emerging property that came out. Until now, the computer scientists, the mathematicians, and whatsoever, still do not really understand why the language model is producing those emerging property, right? So we have to be careful when we use large language model, because it produces certain property that is very interesting that you can use. But we do not know how it works. We don't know what is the upper bound. We do not know what is the lower bound. Now, that actually creates a lot of very interesting things, basically what we call the foundation models, right? And people are creating foundation models because it basically based on a token base. There are many new applications they're developing on this using what we call the foundation models of things like in the robotics itself. And as you can see, there are many foundation models basically built for robotics, right? Groots and from Nvidia, many other models whatsoever. And basically, one of the challenging things in robots is that if you, even for the simplest thing that human can do, like turning a knob, the robots have a challenge doing that. So we need to actually develop all these foundation models for all this kind of stuff. Now, moving forward, let me just skip on this. One very interesting algorithms where people actually didn't talk about it, talk about it many years ago, but forgotten about it, is the algorithms AlphaGo. Remember AlphaGo when it beat Lee Song-do in the Go of games? It is a phenomenal thing. The idea of the algorithm is a very simple idea. It's based on what we call a reinforcement algorithm. The algorithm is simply to punish you when you do it wrong, reward you when you do it right, right? And the whole algorithm, the basic concept of algorithm is that it's just like a kid. When he learns how to walk, it's basically because of that. The same things as what we all do over here. So using such a, of course, before that, of course, to implement such algorithms, although in theory it sounds simple, in practical, it is extremely challenging. Now, this is examples of a robot that is not taught how to put the red pig into the hole, but it is asked to put the red pig into the hole. So what the robot is doing is that it's try and error, making mistakes along the way, and updating its algorithms along the way. So basically what you have is that you have algorithms that's able to learn by itself. Now, with supercomputers, and now you have computers that have thousands, if not 100,000s or even millions of GPUs, now you can actually do simulation. You can run thousands and thousands of simulation to train the robots. Because in the earlier example that I show over here, robots, it takes a very long time to actually train them. So now you have actually machines that are able to actually do that. That outing is not just for robots itself. It's applied into many things. And one of them that you may hear is actually called a large language model called the DeepSeek. The DeepSeek is actually the combinations of the foundation models. Inside there, the training is basically has a very interesting thing, actually using what called the GRPO. Don't worry about it too much, but using reinforcement learning, that actual fact give a world a stun on give the world a shock about how large language models can be trained. Now, this of course goes on to AlphaFold, where Dennis Habibis actually won the Nobel Prize for chemistry last year, right? Now, switch a little bit forward is basically the ideas of agent. You heard the earlier speaker talk about agents and whatsoever, but one of the most important things is that it's able to do decision making and do an action from the agent itself. There are many types of agent. I do not want to go on it too much, just to skip on it. But I just want to give you examples of where a very interesting but funny application. This is typically what we'll do when we graduate or we get fired by our boss. Write a resume, right? Now, typically what you do is that you submit, you will send, after you write your resume, you will send to companies, whatsoever, and hopefully, and you pray very hard that the company will actually reply you and give you an interview. Now, in San Francisco, you have a company that actually produce algorithms, or rather apps, that actually took your resume, automatically look at it, see what are the jobs that's available, apply the job for you, find out where the location, correlated with your location or where you are, and so forth. So automatically, they can apply job for you. So LinkedIn are in trouble, So what we want to do is that, like I mentioned before, we want to do not just predictions. We want also the machines to be able to do discovery, find out new things for us. So in the community itself, the AI community, all right, we are starting to experiment with new things, like trying to build a fully automated AI scientist that's able not just to help us to predict images, how accurate the thing is and whatsoever, but able to do from end to end and produce a new results and so forth. So there are experiments, things like this, like biomedical research and stuff like this. And this is just examples of it. The reshaping is a model for predicting molecules. Again, I don't want to delve on it too much. Let me skip on this. Now, the earlier speakers have spoke about coding, vibe codings and whatsoever. There are many examples of this. As you can see over here, there are many types of it, and it is pretty much a very big industry right now. There's a couple of startups which we actually track. They are in the area of close to $1 billion fundings per company, right? Which actually do this. It's not just about coding itself, but the entire package from coding to software engineering to quality assurance and stuff like this. But what is interesting is that these things together with a lot of things, for example, like the AI infrastructures is getting lower and lower costs. When I say lower cost, is that in terms of per GPU, the cost per GPU is still the same. But the amount of power that it has improved significantly. There's a lot of ones to actually produce much more tokens and so forth. So you could see that the price drops of all these OpenAI, Anthropics, and whatsoever has come down tremendously. Which basically means that we are seeing more and more, we are seeing the collapse of software cost itself. Not that software engineers are going away or developers are going away, but the productivity is going so high that now, as developers, instead of producing 100 lines of codes per day, you're producing thousands of lines of code a day. A couple an order above, or even 2 orders above of codes. Now, the thing that many people will ask, should we get rid of software engineers then? No. In fact, it is very important to have very experienced software engineers, because then the software engineers were able to question the AI. Why is it produce code in this way? Why is it produce code in the right way? Whether is there security issues and whatsoever. So this is, but the important thing, the point over here, is that productivity is going to increase tremendously. So what we could see is that we are, as a programmer, we are going to see a co-pilot that's going to help us. We're going to see robots that is going to write a program itself. And with a lot of AI factories whatsoever, we're going to see robots churning out a lot of codes, so to say. So much so that now we are looking at robots building robots. And this is not just a science fiction. The scientific community are already building algorithms, building ideas on how to build AI to build AI, robots to build robots. So this is a recent paper called the Darwin-Gordian machine. As you know, Darwin is basically evolution, the person who invented evolution. And this algorithm is that it's able to modify itself. So they improve the algorithm by itself. So you will be able, the next version of the algorithms is a better algorithm than the current version. So this is a proposal they put up, and they are early sign of success. It's not human yet. So this is basically what a demonstration of it. The Gordon-Darwin algorithms, and So you will have iteration and whatsoever to actually self-improve. It will write its own algorithms and just self-improve itself and so forth. Right. Now, we talk about, just now we just talked about scientific discovery. Are we there yet? Well, you may think that it's a science fiction, but there's already an app that's been recently been released called Novix. It's a PhD levels agent that's actually fact able to generate out novel research ideas. And from the research ideas itself, what they do is that they go onto the web to do a search, right? They come up with all the ideas, bringing up a map and whatsoever. As you can see over here. So what you do is that you can pick into different ideas, and you can pick them, or you can select what will be the best ideas to whatsoever. Now, on each idea itself, then you will start to build experiment on it, right? The algorithm will start to build, perhaps even includes, that's able to build software codes. There are already new technology whatsoever, build software codes and whatsoever, analyze the data and so forth. And this is an agent. Now, this is still in a very early experimental stage, but you could see that now we are building artificial scientists, so to say. So maybe in a year or two from now, I will not be speaking here. There will be avatar here with this algorithm running in the background. Now, this is a chemistry lab. And many of you who have done chemistry will be extremely familiar with this, all right? Now, the reason why we do all this chemistry in the labs is that we experiment with, we will then write a report, collect data, and whatsoever. It is very, very human intensive, and so forth. So over in China, this is a set up automated chemical analysis lab. And this is how the labs actually look like. So what you do is that you do an experimental submission. Sorry for that, some of that are in Chinese. And then you prepare allow the machine to do sample separation, and then let the experiment start and start collecting data, right? And so forth. So imagine that in the future, what you have is that all these big chemical labs, chemistry labs, that actually be fully automated, right? And some of you may have heard the concept of a dark factory, right? In China itself is a new concept, because now in China itself there are factories that actually have no human inside there, that they do not need to switch on the lights. That's why it's called the dark factory. End to end, just no human being. So the same goes to this. You have what we call a dark synthesis lab. So this is my last slide. I'm a science fiction's buff. One of my heroes is Jarvis, not Iron Man, but Jarvis herself. I was hoping that at some point in time in my lifetime, I will have a Jarvis who can actually help me in doing my scientific work. So with that, I thank you very much.
Thank you very much. Thank you very much. Really exciting. We have 3 questions, and we do have time, so it's great. So question number 1. There is a lot of discussion around the energy consumption of AI, Gen AI applications. What are your thoughts on solving this challenge? Is the future bright, or do we need to start investing in other means of generating required power?
Oh yes, definitely. We are all big user of energy. Some of you will have 1 mobile phone, some of you will have 2 mobile phones, and at some point in time, you guys are doing texting, whatever. Use every pico, every single bits you use uses energy whatsoever. AI, we are in the community, we are trying to reduce the computational needs for each algorithms, but we have a paradox here. The paradox is this. When we make the algorithms cheaper and easier to use and more familiar, there's more people using it. And when there's more people using it, more energy is being used, right? So there is a paradox that we are seeing. So we do have to look for new form of energy. You could hear many of these big tech are looking at nuclear plants, buying nuclear plants, and so forth. Renewable energies, 10 gigawatts, 6 gigawatts, 10 gigawatts, and whatsoever. And we really have the new energy. And we have to find new materials. Because one of the things is that we have to store this energy. So battery technology, solar panel technology, and so forth has to improve over the next couple of decades.
All right. Follow-up question on that. Since we do agree that energy and compute are the bottlenecks, do you see AI designing the next generation of most efficient chips, kind of AI optimizing for itself?
Yes. AI, Nvidia, TSMCs, and everybody is now using AI to design the chip. The chip has become so sophisticated, right? You're talking about 300 billions of transistors inside a single chip, packaged in a small little chip like this, right? There is no way for a human to able to actually design those chips anymore. You have to use artificial intelligence to actually assist the engineers to design those chips. At the moment right now, it's still assisting it as an assistant. I believe that at some point in the future, it will start to design itself.
Cool. You mentioned physics-informed neural networks. What's the biggest breakthrough you've seen when scientists actually trusted the model's prediction over traditional equations?
Well, there are many things. Recently, there was a publication by George Kondowski in Brown University that do a survey on what are the things over here. So there are many things. Like, for example, like this technology is being used to design new materials, right? Also used to design, for example, like artificial hearts and whatsoever. Because in order to design artificial heart, if you do a simulation, it's computationally very, very intensive, right? And it takes many. Now, with such a technology, now you can actually run it 1,000 times faster and so forth. So now you can run a lot of different models. That's allowed us to have advancement in the area of medical science, in the area of material science, and so forth.
Cool. We have time for maybe a couple of more. So what would you advise industries which, due to regulatory reasons, require traceability, auditability, and explainability on AI-produced results?
Right. It is very important. In fact, when I, as a applied mathematicians, I have a trouble working with the AI community because many of these things is unexplainable, right? For those of you who are who works in the area of mathematics, you start off with a llama. First of all, axiom, conjuncture, llama, theorems, and whatsoever before you can actually apply those things. So we as a mathematician, we always have proof that this thing actually works. In AI, it is not. It is all black box. It's all experimental. You put in input, you get the output, and then you tune the parameters a little bit here and there, and you get the necessary outputs and whatsoever. And you find that, oh yeah, it works, and you get a better results. But you cannot explain what is going inside there. Going in the future, we actually need to know that better, because if we are going to use those algorithms, those things in critical applications, we need to understand how it works inside there. And that's why we are trying to work with many of the universities, professors and whatsoever, especially people in physics and mathematics, to develop mathematical algorithms, mathematical formulations, to understand the neural networks better so that we can able to explain and interpret them.
Great. How can we protect copyright and intellectual property from Gen AI tools? How can the copyright owners get fairly compensated?
This is extremely challenging problems, right? I have no answer for that at the moment right now. We have to really, the world have to get together to find a way of regulating this. Because think of it, it's just like your bank notes. You have a central bank where, actually, in fact, everything coming out from the central bank, you trust it, and so forth, and stuff like this. So, using the same analogy, we need to somehow have the World Organization, and that includes not just the government, but also the universities, the private sectors to come together to come up with formulations on how to go about doing this. At the moment right now, the moment you come up with an algorithm to detect whether the things is copied for something else or whatsoever, there will be algorithms to actually, in fact, able to make it, undetectable, and so forth.
Great. And I'll combine the three questions, sorry, but for the interest of time. Singularity. Is it quantum computing? What's going to get us there? What do you think about quantum computing? And if not, what's next after AI?
Right. So quantum computing is very interesting, right? As you guys know, it's based on the quantum mechanics, and the idea and the two important property of it is basically superpositions and its entanglement that allow it to do computation in a very, very different way. Now, there are already experiments, and we are already conducting experiment research in this area where we combine artificial intelligence with quantum computing. Now, until quantum computing has arrived, all the work that we are doing right now is all experiment and simulations. It's so promising. It is promising, the result that is coming out from all this research study. But until we have a quantum computers, the reliable quantum computers, then we can actually, in fact, show that we are able to do the works that, surpass what the current supercomputers actually can do. But it is something that we have to be very wary of. Because if you have, think of it, if you really have a quantum computer, a usable quantum computer today, what will happen? Right? Just do a mind simulation, right? A mind experiment. If you have a quantum computer today, in combination with artificial intelligence, what will happen today, right? And what are the potential pitfalls that we will get in? So the community have to get together to actually study all the different type of phenomena. What are the things that it will able to create? What are the things that you're able to do? And then we design way of mitigating all the potential risks that we will see.
Thank you very much.
Most
it's been
welcome.
Wonderful having you here.
Thank you.
Thank you. Thank you.